system representation through the method of enumeration. So what we'll talk about is the state space. The system is composed of n elements, and let's say each element is binary in nature. So let the state 1 be that it's working or in an up state, and let the state 0 be for it's failed or it's in the down state. So I can have the performance indicator for each element xi. So that's equal to 1 if the element is working, and 0 if the element is not. If time was an important aspect here, which it often is, so that's implied. So if xi is 1 at time t, that means the time to failure, which we haven't discussed, we will in a week or two from now, that is greater than small t. So the random time to failure of element I exceeds small t is the same thing as saying xi is equal to 1 at time t. This we could do for all such elements of the system. So if the elements are binary in nature, then we would have 2 to the power n, the entire power set of such states, and that would, each of those points, each of those 2 to the power n points would give me a state for the system itself. So if the system is up or if the system is down, we would be able to indicate that, provided we know how the system is composed of in terms of its elements. And this works, and we are going to look at an example in the next slide. For small systems, this works. In fact, later on we are going to look at also a three-state system through enumeration. Let's look at the example. It's a simple structure. Let's say we have a bridge system. The bridge system is composed of 7 elements, 2 piers, 1 deck slab, and 4 girders, and which means there are 128 possible states of those elements, and each of those would give rise to an up or down state for the bridge system. So let's look at a few of them, and that would give us an idea how this method works. And obviously, in creating this enumeration, one needs good structural knowledge or good knowledge for the system. So let's look at the first row. So all the elements are up, so from pier 1 all the way up to girder 4. So obviously the bridge system is up. The next one, let's say the pier 1 is down, it has failed. So regardless of the state of the other elements, it's an essential component of the bridge system. So obviously the bridge system has failed. That's the second row. The third row is likewise what happens if pier 2 fails. While all the others are up, then also the bridge system fails. Obviously, if both piers fail, that would be another row down the road. Then also the bridge system would have failed. If we look at row number 4, if the deck slab fails, the bridge has failed, even if all the others are up. Likewise, the next row, row number 5, if girder 1 has failed, that means failure of the system. The girders are numbered from left to right or end to end. So if it's one of the end girders and it has failed, then the bridge has failed for all practical purposes. So that's row number 5, but it could be, and that's what I think is happening to the bridge here, that's our understanding, is if in row number 6, if girder 2 has failed and everything else is up, then the bridge is able to take that loss and still function. So even if girder 2 has failed but the others are up, the bridge is up. That is what we find here. Obviously, it would depend on the bridge's behavior, on its design and construction, but that's one of the things that will come out only from our understanding and analysis of the mechanics of the system. The next row, likewise, we make the same argument that if girder 3 fails, another interior girder, and the others are all functioning, then the bridge will still be okay. Again, the next row, if girder 4 fails, then the bridge has failed because it is one of the end girders. This way, we could enumerate all the states of the system, and if the number of states is small, it's actually a feasible method until we have exhausted all the 128 possibilities, the last row being all of them are down and the bridge system is down as a result.